Okay, good morning everyone. So welcome to today's class. Today we will continue to introduce the multi-layer perceptron. Recall that in last class, actually we already finished learning what is the multi-layer perceptron neural network, what is the general structure or general architecture for the MLP, and we also learned the updating rules. That is given MLP how to update all the parameters, but note that all the updating rules are already based on that. We use sigmoid activation function, and we use that error loss with the square loss. So note that we must follow this assumption, then use gradient descent, we can get all these updating rules. So today we will continue to learn how to implement the MLP from scratch. And this MLP implementation is specifically for such a structure. So only for this structure, we have one input layer, one hidden layer, one output layer, and the number of nodes are 2 to 1 in these 3 layers, and also the activation function is sigmoid activation function. All right, so let's review. In this constructor, we have initialized all of our parameters, wij, wjk, tj, and tk. So here I just illustrate them using the matrix. So that's mathematical matrix, not array. Because when we define this array, actually all of them are 2D arrays. But here I just omit the 2D because I just use the matrix or vector to represent them, because later on we will see the computations. All right, then we also learn the sigmoid. Sigmoid, it's not only outputting the sigmoid. When it's in backward propagation, it will also output the derivative of the sigmoid, because this will be used later on to do the gradient descent, right? So we use this sigcal to indicate whether we are in forward propagation or backward propagation. If it's forward, we need to return sigmoid. If it's backward, we need to return the derivative of this sigmoid. Then we go into this forward propagation. Forward propagation, let's see what happens in this code, like what computations has it done. First, we reshape X to be a sample. Now sample is a 2D array. Actually, it also contains the same values with X with our input data, but somehow we reshape it because later on we need to use such shape to 1 shape to perform some matrix multiplication. So now we have that X, okay, it's already sample, so we denote it as sample. Our sample is such a vector. It's a 2D vector, but I just use the vector denotation, the mathematical denotation. All right, this is our sample. Then first we compute the hidden node outputs. That's all of this yj here. Let's see what happens in this yj. First, we do a dot product. We use wij to perform the dot product with sample. Let's see what will happen. So wij, we know that is this one, this matrix. Sample is such a vector. If we do the dot product, so that is, here we try to get this wij dot product with sample. Then after some simple mathematical computations, you will see that it's just this W1, W2, W3, W4. Then dot product with this X1, X2. Right? This is what happens in this step, dot product. And then we just try to perform the dot product. We know in this dot product, it should be the row vector dot product with the column vector. That should be W1 times X1 plus W2 times X2. And then the second element should be W3 times X1 plus W4 times X2. Now we find this dot product is exactly the weighted sum of the 2 hidden nodes. Right? If you refer to the previous structure here, for this hidden node, this weighted sum sigma 1 actually is just exactly W1 times X1 plus W2 times X2. Until now, we haven't added theta. Later on, we will add it. And for this second hidden node, its weighted sum is X1 times W3 plus X2 times W4. So know that after this dot product, it exactly stores the weighted sum of the two hidden nodes. All right, then let's see what will happen next. Next, we add this dot product results with the Tj. Tj, we know that it exactly stores theta 1 and theta 2, the bias parameters for the hidden layer. So that means, okay, Wij dot sample. Next step, we add Tj. So after that, it means that this should be added with theta 1, theta 2, which we can try to modify here. So now it becomes this sum after we add this Tj. And next, we pass it to sigmoid function. And we're letting this equal to be true, means that, okay, now we are in the forward propagation. So this sigmoid will return the sigmoid value, this one, taking the weighted sum as the input. And that means this Yj actually is what we want, right? This Yj is the hidden node's output. It's a 2D array with a shape 2, 1 because we have two nodes in the hidden layer, so we must have two values here for this Yj. And so that's why here we can simply use a dot product to represent the weighted sum to implement it. And actually that also explains why previously we want to maintain the dimension of all the parameters. So we want to let them all of them to be the 2D arrays, because after the to be 2D arrays, actually later on the computations will be quite compatible. Okay, we have the Yj. Yj stores this output we want. So next we try to get this Yk. So let's see what is Yk. Yk, we first get the transpose of Wjk, and then we use this transpose to dot product with Yj. So let's see what will happen in this step. Maybe we can score this one up. Okay. All right, so next, let's see what happens for this Yk. Yk, first we get Wjk transpose. What is Wjk transpose? So let's transpose, just use T to represent that, and then dot product with this Yj. Wjk is W5, W6. Previously, it's a column vector. Now, after transpose, it becomes a row vector. So it becomes W5, W6. Then dot product with Yj. We know that Yj is something like after sigmoid. So Yj exactly stores what we want, the output in the hidden layer. So it's Y, just denote it as Yj1. Yj2. Then what is this dot product? This dot product is a matrix with shape 1, 2 with another matrix with a shape 2, 1, right? So after that, it should be W5 times Yj1 plus W6 times Yj2. Just get this value. But of course, in the Python implementation, actually what we get will be stored in a 2D array. All right, this is after the transpose and dot product. And next, as you can see, we add it with self.tk. And what is self.tk? Theta 3, the bias parameter for the output node. So we add it for this one, add it with theta 3. So that means theta 3 added here, and then theta 3 added here. And if you look at what we get here, it's exactly the weighted sum for the output layer, right? So we try to look at this structure. For this output node, the weighted sum should be W5 times YJ1 here, plus W6 times YJ2 here, then plus its own bias parameter theta 3. This is exactly the weighted sum. And of course, next we also need to pass this weighted sum to the sigmoid function to get the true output. So here is the outermost function is sigmoid, and also the sigcal must to be true because now we are in the forward propagation. So, all right, after that, we make sure that the YK is what we want, the output knows output. Or actually, this is the final output of the MLP, right? So what we get for this YK will directly be output from the whole MLP model. And note that even though we just use one value here in the mathematical computation, but what we implemented here, actually YK is a 2D array with the shape 1, 1. So even though it only stores one value, but still it's 2D, has the shape 1, 1. All right, so until now, actually, we finished the forward propagation computation. Everything has been done, but still we have another indicator that is predict. Because we want to know currently whether we are in the training stage or testing stage. If we are still during the training, then we have to output all of these middle nodes outputs. So if predict is false, then we are in training. Then we return sample yj, yk. That means the input, we need to store it. The hidden nodes output, we need to store it. And the final output, we need to store it because all of this should be used later in the backward propagation to update the parameters. But if we are in the testing stage, that means now if predict is true, then that means finish training, no need to store all the middle results, directly return the final output yk. So basically, we just use this indicator predict to try to separate the two cases. Because during the testing, if you want to predict for the testing data, you don't need all the middle results. You only need the final result. All right, so this is the forward propagation. Any questions so far regarding the implementation of forward propagation? Great. Yes, here the keynote is here. Is try to get familiar with such dot product implementation. So the weighted sum, actually most of the weighted sum can just be implemented using the dot product or some matrix multiplication, which is a very efficient implementation, so that you don't need to explicitly multiply these things up and then add something. If you want to do that, then possibly you will need some hard code, or even you need to use some for loops to do that. But actually, you can just efficiently implement it using some matrix multiplication. Very convenient. All right, if no question, then let's move on to the backward propagation. This backward propagation, it takes two arguments. The first is values. What is values? Values is the tuple. It's a tuple consisting of three things. Actually, values, this tuple is exactly the output of forward propagation. So in forward, if predict is false, we return a tuple, right? Sample yj, yk. This tuple will be the input for back propagation. So values is just such a tuple. And you can see we first try to extract the inputs and hidden outputs and final outputs from this tuple value. So we get, okay, big OI should be the value 0, input sample. OJ is values 1, which is our hidden node outputs, and then OK is values 2, our predicted output. These three items are exactly what we returned in the forward. And now we also have another argument, big TK. What is this big TK? Of course, it's target, our true label. And because we need to measure the error when we try to compare the computed output with the target, so we must also compare it with this big TK. This is our target. All right, now we are quite clear about what we are facing with these arguments. Then let's see how to implement the whole backward propagation process. So back propagation, we know according to our formula, the first step is that we should get delta k. Delta k, the formula is that it should be OK times minus tk times OK times 1 minus OK. And just to make all of the dimensions consistent, just assume all of these actually are 2D arrays. So it should have the shape 1, 1 because delta k will only have one value, right? Then next is just try to implement this thing. Implement this thing, we get the multiplication between two terms, OK minus tk, with the sigmoid OK. What is this sigmoid OK? If we look back at the sigmoid, by default, the sigcal is false. So by default, it goes into this return command. It returns z times 1 minus z, the derivative of sigmoid. So that means for this thing, it returns OK times 1 minus OK. Right? So by default, it's some backward propagation, and this is exactly corresponding to that term, OK times 1 minus tk, the derivative of sigmoid. And after multiply this OK minus tk, we get delta k. This is what we want, stores this value. All right, then according to this delta k, we can next compute delta j. According to the formula, we know that, okay, now delta j should be oj times 1 minus oj times delta k times wjk. Note that actually, according to the formula, we have a sum here. But for this specific structure, because we only have one node in the output layer, we don't need to do the sum. We just omit the sum. And this delta j should have the shape 2, 1, because we have two hidden nodes in the hidden layer. So we store two values, that is the delta j for the first hidden node and delta j for the second hidden node, the two nodes, delta j1 and delta j2. Then let's see what is this delta j. Delta j actually is, again, a direct implementation. First get the sigmoid oj. We know sigmoid oj by default is backward propagation, so it's oj times 1 minus oj. And then we multiply it with delta k 0, 0. Actually, delta k only stores one value, right? It's a 2D array with shape 1, 1. But to retrieve this one value, we just use some index here, delta k 0, 0, and times self.wjk. So we just multiply these three things up, and then exactly this thing. So this is the delta j we want. And note that it's a 2D array because the oj itself is a 2D array with shape 2, 1. Previously, we returned this oj from values 1, and oj is exactly this yj actually, which we computed just now. In forward propagation, it's 2D array with shape 2, 1 with like oj1 and oj2. So after that, we have this delta j stores the value for delta j1 and delta j2. And then next, with this delta k and delta j, we are ready to update all the parameters. So let's see. wjk. Wjk, according to the updating rule, it should be O wjk minus eta times delta times oj. Again, it's just a direct implementation, so it should be subtracted from itself by this self.learning rate times delta k 0, 0. We retrieve this value times oj. And after that, self.wjk is a 2D array with shape 2, 1, because we know wjk basically is just this one, w5, w6, right, with the shape 2, 1. And next, we update the theta k. Theta k here is theta 3, the bias parameter in output layer. So self.tk should be subtract itself from self.learning rate times delta k. After that, we finish updating the parameters between hidden and output layer. We continue the back propagation. The back propagation is the next step. We need to update wij. Wij, according to the updating rules, should be wij minus eta times delta j times OI, it should have the shape 2, 2, right? Because Wij, this one, stores W1, W2, W3, and W5. And here, we first get the thing that it should subject from, this is self-dot-learning rate times delta j dot OI transpose. Let's try to expand this term. What is this one? So now we are in the backpropagation, and we do this in delta j dot OI transpose. So for this in delta j, we know that actually it stores two values, delta j1 and delta j2, because we have two nodes in hidden layer, and then dot product with OI transpose. What is OI? OI is our input. OI is sample, right? OI is exactly this sample here, but we transpose it, so now it becomes x1, x2, and after that, this dot product actually is a matrix multiplication, because now we use a matrix with the shape 2, 1, dot product with a matrix with shape 1, 2. The resulting matrix should have the shape 2, 2, right? So what's inside? Basically, just we do some pairwise multiplication. The first element is delta j1 times x1. The second element is delta j1 times x2. And then this one should be delta j2 times x1. This one should be delta j2 times x2. This is the resulting matrix. After the matrix multiplication, we get this thing. Okay, after that, for this dot product results, we multiply it with the learning rate. Of course, we need to multiply it with the learning rate, because learning rate adjusts the distance that we want to move, right? But let's further check, is it correct? Like after we get these four values, are they correct? The adjustment or the change to W1, W2, W3, and W5? Let's try to, again, let's check the structure here. If we want to update W1, and we know that whenever we want to update a weight parameter, we want to first find which nodes does this edge connecting. W1 connects X1, the first input node, and J1, the first hidden node. So that means if we want to update W1, we must use the input from X1 and use the change of parameters in J1, which is exactly delta J1 times X1. And actually, they have the 1-1 mapping. So that means this delta J1 X1, actually, it must correspond to W1. And delta J1 X2 times X2, if you refer to that structure, you will find that W2 connecting the nodes X2 with J1. So this change should be added to W2. And then for W3 connecting X1 with J2. So this change should be added to W3. And the last one, of course, W4, because we know that the edge W4 connecting X2 with J2, the second input node and the second hidden node. So you must do this 1-1 mapping, right? We must make sure that the change to the parameters indeed matches with the edge, indeed match with the weight parameters. And after checking them, we find that yes, they are indeed 1-1 mapping. These four values, the changes, actually map with what we defined Wij, W1, W2, W3, W4. And that's why we update it like this. Use this dot product. All right, now we already make sure that this S is correct. So S is exactly corresponding to this thing. The corresponding delta J times corresponding OI. And then the next thing is, of course, we just let the self.wij subtract this term S. And then we get the updated wij. Of course, you can just try to combine the two steps together. Or not combine the two steps together. There is alternative implementation for S. You can also use this one. Self.learning rate times delta J directly times OI dot T. After that, you get exactly the same results. What is used here? Like if the second implementation, if we use delta J directly multiply, we know this represents the element-wise multiplication in NumPy multiplied OI dot T. What happens, and Y is still the same thing by broadcasting, right? Delta J, again, we can try to get that delta J, if we expand it, is delta J1, delta J2, and then we multiply it with x1, x2. So this is the element-wise multiplication. This column array has the shape 2, 1, and this row array has the shape 1, 2. If we want to do some element-wise multiplication, we need to check broadcasting. And we find that 2, 1 and 1, 2, they can be broadcast together because they're compatible. And after that, it should repeat itself so that resulting array has the shape 2, 2. And then for repeating itself is that for delta J, it copies itself to another column. And for x1, x2, it copies itself to another row. So at the end, it works as if we have something like this. So delta J1, then delta J2. It works as if it copied itself. Then element-wise with x1, x2 copy itself. And after that, you will find exactly this element-wise multiplication should be the same with this dot product results. So these two implementations, they are equivalent for this case. So they equal with each other. So that's why we have some alternative implementation here for this S. But anyway, it's okay. Then we get self.wij updated like this. Okay, now we only have one last thing to update, self.tj. That's theta 1, theta 2. This is relatively easier, theta 1, theta 2. Basically, it does not depend on input, right? All the bias terms, they do not depend on input. We only need to subtract itself from learning rate times delta J. And then we are done. So this is the whole backpropagation. Whenever it receives the tuple values, that's the input, hidden outputs, final outputs, and with this target TK, big TK, we can follow this way to update all of these parameters. All right, so any questions so far regarding the implementation of backpropagation? Great. If no question, we need to continue. Because even though we already have forward propagation, we have backpropagation, we are not done yet. It's not a training, right? If we want to implement the training process, we must explicitly program the whole process. And of course, we need to go into some nasty loops here, the train. So we need to try to combine them together. So for this train, we have our training data, big X, training labels, the targets, big T, and then the training, of course, must be some nasty loops because like we have epochs. Inside each epoch, we have all the steps. We need to input all of the training data into the MLP. So first, the epochs or the runs for I in this range self.max round, so that means we will just perform the training for at most max round iterations or epochs. Inside each epoch, we need to pass the whole cycle of training data into MLP. So for J in range M, M is a global variable, so later on we will define M to be 4. That is the number of training samples. But of course, you don't need to hard code this M. Basically, you just need to get M from X shape 0, right? But anyway, here we just hard code it. Okay, M is 4, so M is the number of samples. And then we print some information to let us know, okay, now it's in this iteration and this step. And then inside each step, we know MLP training is just we perform one forward propagation, then one backward propagation. So first do the forward. Let values be self.forward xj. We give the J's training data as input, perform the forward, and return the tuple values. Recall that these values stores the data itself and the hidden outputs and final outputs. After we get these tuple values, we do backpropagation. Backpropagation, we give this tuple to its values and the target big TJ and run this self.backpropagation values TJ. And after that, we finish the backpropagation. So even though the implementation of forward and backwards, they are both a little bit complicated, but the training process is quite concise. It's just some nested loops inside each step. Do one forward, then do one backward, and we are done. All right, so after this max round iterations, we will finish the training. And then we can try to print the final information. So after training, we can print all of the parameter values, use this one, just to retrieve the instance variables. So this is the train process. And then outside this class, our multi-layer perceptron class, we can form our training data X. So we know that input data is just this 4 data, and target values 0, 1, 1, 0 corresponds with the training data. Recall that it's an XOR logic relation, so this data is not linearly separable. Then we create an object from our multi-layer perceptron. So we create MLP from the multi-layer perceptron, and then we call this train function MLP.trainXT. After we run this line of code, it goes into the function here. Train receives x and t, go to training, and know that it will train for 10,000 rounds because we set max round to be 10,000. So it just train 10,000 rounds and stop. So it may take some time to finish the training. And after finish training, we can print all the parameter values. So let's see what are the final values of this MLP, and now we can do one more step of the forward propagation. Basically, that is prediction. We want to predict for all of our training data. So for K in our range M, let big OK be MLP.forward XK true. This true is the predict to be true. So if predict is true, then that means we go into the testing. We will only return the final output YK. No need to return this tuple. Okay, so we can return this YK, and after that, we can print, okay, what is this YK? The computed output for each of our training data. If you run these codes, then you will get exactly the same results here. After 10,000 rounds of training, you will get the parameters like this. And in the next round, you do one more step forward propagation, the prediction, you will get the results like this. And know that you will get exactly the same results because there is fixed initialization. We use the same initialization, right? We hard code the initialization. So after the initialization, there is no randomness in the whole algorithm. So you must get the same results. But of course, You can also try to write some random functions here to generate all of these parameters. If you randomly generalize the parameters, then your ending results will be different, because starting with different initializations, the MLP might converge to different local minima. In that case, you will get some different results. But if you fix the initialization, of course, you will get exactly the same results. All right, so any questions so far regarding the whole implementation of MLP? Great. If no question, any question? If no question, then maybe let's take 5 minutes break. Maybe you'll need some time to absorb all of these implementations. After 5 minutes break, we will continue. Previous values into some string.
Okay, so I need to switch these to
Yes.
numbers?
Yes.
But
Integer numbers.
am I supposed to do it on a specific data scale, like a data frame, or am I supposed to use a different data frame than
I think
or wasn't sure?
it doesn't matter so much as long as the final return you have encoded is the return one.
Okay.
Because later on, I think we don't need the previous year.
Okay, so we need the first three columns to be encoded, and so it should be replaced.
Yes,
Okay.
replace with the integers.
Okay. Thank you so much.
predict the default 是 false。就是你回到那一步，回到刚刚那个 for。对，这里你可以看到 predict the default 是 false，就是我们不 assign 任何 value 的时候，它就是 false，除非我们让它是 true，它才能是 true。所以在 train 的时候，就是在这一页 train 的时候，我是不需要下一页 train 的时候，我是不需要给它一个 predict 值，因为 by default，这个 for 的时候 by default 它是 true，它是 false，就 by default 的这个 value 是个 true。对对对。对对对，如果 true 的话，那就不开了。这个就只做 prediction，就不需要再做 value。对对对，就之前的 print 是来形成的。再往上。
I need to calculate the mean for the specific column.
对对对，但不是 exactly 就是那个一样的语句，但是 print 出来的只是这些。
If you do that, does it get the mean of the whole data frame or columns? I will be. Did you do it?
All right, so let's come back to the class. Yeah, and I need to scroll down this screen again. Okay. All right, cool. So now we already know like how to implement this MLP structure from scratch. But of course, this only specifically for this structure. So if you change the structure, like for example, if you add one hidden layer, or if you change the nodes of each layer, then the implementation will be different because we already fixed all of the shape of the parameters like this. Then another note is that, again, I need to remind you that these formulas only apply for the arrow function looks like this and use sigmoid as the activation function. So if you use a different arrow function, or if you use a different activation function, then all of these don't apply. Totally change. Because if you change different loss function or activation function, then you need to differentiate the arrow function again. Because all of these are based on gradient descent. Gradient descent means that you differentiate the loss function, and you will get very different updating rules. Then how to differentiate the arrow function? Basically, that's something similar to what we demonstrated in the supplementary notes. If you check the course website, you will find that we provided supplementary notes to tell you the mathematical details, that is how to do the computations to get the gradient descent results. You need to do something like that. But of course, it's totally fine if you don't know, if until now you haven't learned how to differentiate the functions, like it's supplementary notes, so we won't require you in the exams. Actually, it's totally fine. Later on, I think after you take some math courses, you will know how to like differentiate the function. Then at that time, you can know how to compute the gradient descent for any given loss function by yourself. Yes, for COMP2211, we don't cover that. If you're interested in that, later on, maybe in the future semesters, you can take COMP4211 machine learning. For that course, you need to manually calculate the gradient descent, manually differentiate the loss function, and then try to derive the updating rules by yourself. That's what you need to do in COMP4211. Yeah, many students suffered a lot in COMP4211 in this process. Okay, yeah, this is but for 2211, you don't need to do that. We will always provide you with the updating rules. All right, then until now we have seen a relatively simple structure of MLP. We only have like one hidden layer, and we only have two hidden nodes, one output node. Next, we will see a more complicated MLP neural network, which we will use to do the handwritten digits recognition, a very classical task in image processing and computer vision. So let's see this handwritten digits recognition. So basically, that's given some inputs, that's the imaging inputs, which consists of the handwritten digits. We want this MLP to recognize or to classify the handwritten digits. So like here, if it accepts an image like this with 784 pixels, and then after the neural network, we want it to output the correct class. So let's see more terminologies before we build our MLP to do that. Review some of the previous terminologies. Recall that in the artificial neurons, we introduced two terminologies. The first is learning. Learning is the process of updating parameters in the neural network. And we introduced a second terminology, epoch. Epoch refers to one cycle through the full training data set. And here we introduce some more terminologies. Actually, I think we already used lots of times these terminologies. Training data, right? We say it always, all the time. Training data refers to the data our model learns from. Sometimes we will split the training data into training and validation data, so that we will train on the new training data, and we will test using the small validation data during the training. So that means maybe after some iterations, we just do one testing in the validation data to try to monitor our model training performance. Testing data is the data that is kept secret from the model until it has been trained, and testing data is used to evaluate our model. So that means usually the testing data cannot be disclosed to the model before it's finished training. The training only uses training data, and during the prediction, we use testing data. You can just imagine that the training data are the lecture notes, and the testing data are exam papers. Of course, we won't disclose the exam papers to you until you come to the exam. Right? You can only train yourself from the training data, from the lecture notes. Yeah. And the training data, so typically it's non-overlapping with the training data. So we need to make sure that there is no data reviewed. And then specifically how to evaluate the model if we have a testing data. Actually, we have already learned. In default cross-validation, we learned model evaluation, right? So that means we have many metrics to evaluate the model, like accuracy, precision, recall, F1 score, MCC score. All of these metrics can be used to evaluate the model. The next terminology is loss function. Loss function, previously we introduced one loss function is here. This is a loss function. But actually we have many other choices of the loss function. So loss function is a function used to do differentiation, to update parameters during training. So basically, if we want to get updating rules, then we have to differentiate the loss function. And loss function is used to monitor each epoch to decide the convergence during training. Because for each epoch, we can check the value of the loss function. And if we find that the loss function values converge, then basically we can conclude that the model training converged because the loss function doesn't change. And loss function can also be used to quantify how accurate a model's predictions were by computing the loss function on some testing data. And note that the loss function is very important. We can see loss function is crucial for neural network because the only objective of the neural network is optimizing or minimizing the loss function. Loss function is the goal, the objective for a neural network. Actually, you do all of these things, you derive all of the updating rules just because you want the neural network to minimize the loss function. This is the only objective of the neural network. And then how to update that? How to make sure that the loss function is optimized properly? We need to use some optimization algorithm. So optimization algorithm, it controls exactly how the parameters are adjusted during training. Even though we know we have objective optimizing the loss function, but how to do that? The methods differ. Like in our lecture, we introduced gradient descent. This is an optimization algorithm used to adjust the parameters used to minimize the loss function. But there are many other optimization algorithms, like stochastic gradient descent, like Adam, like many other algorithms. But note that almost all of the optimization algorithms, they are based on gradient descent. So they are just some improved version of the gradient descent. All right, so these are some new terminologies. Any questions so far regarding the terminologies? Great, even though we use them all the time, but yeah, until now I just introduced these terminologies because these terminologies are really important for neural network. Then next, let's see our data set in this handwritten digit recognition task. So we will use the MINIST data set. This data set consists of two sets of samples, training data and testing data. So it already split into two sets. The training data, of course, is very large. It has 60,000 images of handwritten digits from 0 to 9, and testing data has 10,000 images. All of these images, they are already pre-processed such that they have the same shape, the same size. So all of these images are 28 pixel by 28 pixel, including training and testing. So they are already processed to be the same size. And the data set just looks like this. It consists of all of these handwritten digits. Then what are the procedures if we want to build a neural network, MLP neural network, for this handwritten digit recognition task? We have these 10 steps to do. First, we need to import the required libraries and define global variable. Then we need to load the data. Then we need to explore the data a little bit because to train your model on a data, actually the premise is that you need to know your data very well. Then after we explore the data, we are already familiar with data, it's time to deal with the model. So first we build the model. Then we compile the model. Then we train the model. After we train the model, we already have a finished model. Then we can evaluate the model accuracy using the trained model. After that, if we find the model is good, then we should save the model, because later on we might use the saved model to do some new predictions. And so next we can use the model, and then we can also try to plot the confusion matrix for our model. This would be the procedures, and this will be the task for the remaining time of this class and also for the next week's class. Because to finish these steps actually require some time. So step 1, import the required libraries and define global variable. You will find that when we go into the neural network, there are many libraries you need to import. Much more than your previous, like the naive Bayes, like the k-means. Because usually to build a neural network, you have to rely on the existing modules. For such a big, possibly a big MLP structure, I don't recommend you to implement it from scratch. From implementation from scratch is okay. Like for our previous model, you only have one hidden layer. It's still okay. But for this model, don't recommend you to do that. So please just refer to some already existing libraries, some modules, and just import them to use them. So let's see what libraries we need to use. Definitely we need NumPy. We always need this one. We will need this matplotlib library because later on we want to do some visualizations. So we also import this library. And then this cbone will be used to plot the confusion matrix later on. Pandas, we also need that. We need pandas to try to manipulate our data a little bit. Math, because we need some math. And datetime. Datetime, this is a useful library, can review the current date and time. Later on, you will see why we need that. Basically, we need this to add some timestamp to our model. And then the most important library we will use in this task is Keras. Keras, as introduced in the first class, Keras is a library very suitable for beginners to implement some neural network. So from keras.datasets, we can import this dataset minlist. And then from keras.models, we import sequential. Sequential in Keras means neural network. So whenever you see this sequential, this keyword in Keras, that means it's a neural network model. And then we import dense and flattened layers from this keras.layers. Later on, I will also explain what is dense, what is flattened. And we import some regularizers. This will be used during training. And then from the TensorFlow.keras.optimizers, we import Adam. Adam is an optimization algorithm. And we also import one thing called sparse categorical cross entropy. This is the loss function we will use to train our MLP. So just now we learned the terminologies. Cross entropy is the loss function. Adam is the optimization algorithm. And the remaining thing will just be some library that we use to create some tensor boards so that we can record our training history. The next thing, and also the confusion matrix we import directly from the TensorFlow.math. And activation functions, we don't need to implement it by ourselves. We can import the activations from the TensorFlow.keras. And we define a global variable epochs to be 1. So that means we will only train our model for 1 epoch. All right, this is step 1. Import all the libraries we required. Then step 2, we load the data. So load the data. Recall that previously we already implemented minlist from keras.datasets because this is a very famous, very classical dataset. Almost all the neural network libraries already imported it, already had it. So you don't need to download the data. You directly import it from Keras. Then use this function minlist.load data. After that, you will get a tuple like this. You will get X train, Y train, X test, and Y test. So that's the training data, training labels, testing data, testing labels. And then if you print their shape, you will find that X train has a shape 60,028. Means that we have 60,000 training data. Each of the training data is an image with 28 pixel by 28 pixel. And then our Y train, our training label has the array 60,000 is a 1D array. It just stores all the labels, the true labels for training data. Now that in this array, all of the values are some integers from 0 to 9, because in total we have 10 digital, right? Digital numbers from 0 to 9, representing that 10 classes. Then testing, we have 10,000 testing data. So the Y test also has the shape 10,000. All right, after that, we load our data. Next step, try to explore our data a little bit. So we can select one data, because we have so many data. We have 60,000 data. Let's just try to extract one data to see what's inside. So we get this one, the first image data from X train 0, and we can first use the pandas data frame to show that. Since it's image with 28 by 28 pixels, so if you look at this pandas data frame, it has 28 rows and 28 columns. Each of the entry is an integer from the range 0 to 255. That's the intensity of the pixels. So as you can see, there are some values. You may not see it clearly, but all of the values, like all of the entries stores the values. Actually, they are roughly a shape of 5. Most of the pixels have the value 0. With the values, like they roughly have the shape 5. Actually, it's just this one. So we can also use this matplot library to show the imagery. Like just run this show function, and then we can get that. Okay, this is the first training image, 5. We can also try to display more images. So suppose now we just want to display 25 images from the training data. So we can use this matplotlib like this, and then we can show off our first 25 images like this. As you can see, there are just some handwritten digits. So after that, we explored our data a little bit. Now we already know, okay, what are our data? They are just images. We know their size 28 by 28, and we know they are grayscale image. Each of the pixel only has one intensity value from 0 to 255. After explore the data, we can go into our model. So next is build the model. Before you use some libraries to build your model, of course you need to first design your model. Design what your model looks like. So instead of building the model from scratch, we will directly use the software library Keras. Because if you look at our design, we have 2 hidden layers. 2 hidden layers, each layer has 128 neurons. There is no way for you to implement from scratch. If you want to create some weight parameters using this hard coding way, no way to do that, okay? So directly use the Keras. So let's see the design. The design, first we have a flattened layer. The flattened layer is crucial for this task because previously we have 2D images. Our image is 28 by 28. But the MLP model, if you look at the architecture, you find the input layer must be 1D, right? All of the input nodes, they are just be some column vector like that. It cannot accept the 2D inputs. So the first step is that we have a flattened layer, try to flatten 2D images into 1D. So maybe we can try to visualize just to have a sketch of the structure. this is the input image, 28 by 28 pixels. And our layer 1, the MLP's input layer is try to do a flatten. After this flatten, basically it just tries to convert 2D to 1D, flatten everything, and then we will get something like this. This is our layer 1. After flatten, here in this layer we will have 784 input nodes, because here 28 times 28, 784. Just each of the pixels now is flattened into this 1D layer. All right, after this layer 1, actually that's our input layer for MLP, we know that. We go into our layer 2. Layer 2 is our first hidden layer. Now it has 128 neurons and ReLU activation function. Here comes a new activation function. After I introduce the whole structure, I will elaborate what is this ReLU. So let's just try to draw the structure. So next we have hidden layer. That's our layer 2. Actually, that's the hidden layer 1. And we have 128 neurons. We also notice one thing. We call it dense layer. What is dense layer? Dense layer means that each node in the previous layer must be connected to each node in this layer. Dense means fully connected. So like this node must be connected to each of the nodes here, and also for this node, for each of the nodes, they must be connected pairwise, dense layer. So as you can see, how many edges are between these two layers. That's 784 times 128. This number of edges here, each edge is associated with a weight parameter. We know that each edge is just one weight. That means until now, we already have 784 times 128 weight parameters. And bias parameters, until now, we already have 128 bias parameters. Because for each of the node here is a neuron, the neuron itself has a bias parameter. Not finished yet. Layer 3, our hidden dense layer 2. Again, we built it with 128 neurons and ReLU activation function. So go into the next layer. Our hidden 2, 128 neurons. Dense layer again, fully connected. So each of the pair of the nodes must be connected together. Okay, note that after this layer, we increase 128 square weight parameters and another 128 bias parameters. So as you can see in an MLP, it's a very big model. There are so many parameters. Each of the parameters, they need to be trained, they need to be learned, updated. Finally, we go into our output layer. Output layer is another dense layer. We have 10 softmax outputs. Means that in this layer, we have 10 nodes. Each of them use softmax activation function. Again, later on, I will introduce what is this softmax. Let's try to draw it. Output layer, we only have 10 nodes. Since only 10 nodes, I just explicitly draw all of them. This is output with 10 nodes. Is a dense layer. Dense layer, so each of the node here must be connected to each of the node in output layer. I just omit the edges. There are so many edges. Just use this one to represent. Okay, it's a dense layer. 10 outputs here. And after this output layer, it will be the final outputs. So this MLP has 10 final outputs for each of the input image. So anyone knows why we need 10 nodes here? Even though you don't know what is softmax, but still you can guess why we have 10 nodes here. Yes, because 10 numbers. Because we are doing a multi-class classification problem. In total, we know our digits numbers are from 0 to 9. So actually, there are 10 classes in our multi-class classification. So we have 10 nodes in output. Actually, we get 10 outputs. So this output layer represents the guess. So that means the zeros output, this node here, represent the probability that the input digit is 0, and the first output, this node here, represent the probability that the input digit is 1, etc. So the final output in this output layer represents the probability. So that is what we get here. The value is the probability of the input is classified as 0. The second one is the input classified as 1, and so on so forth. The last one is the input is classified as 10. So we have 10, 9. This is 9. So we have 10 probabilities here. We want to classify the input image into 0 to 9. Okay, so this is the structure of our model. We designed it like this. At the end of the MLP lecture, I will give you some hints, explanations why we design it like this. So currently, you just need to know that we design it like this with these layers and so many hidden nodes, and the output nodes are quite clear. We have to use these 10 output nodes. But still, we have some things unclear. What is ReLU activation function? Actually, we now have 2 new activation functions. What is ReLU? What is softmax? Let's try to get ReLU first. ReLU activation function, the full name is called rectified linear unit. The mathematical formula is very simple. Fx is max 0x. So ReLU is just something like that. So that means if x is positive, then it's a linear function. It's directly x. If x is negative, then ReLU outputs 0. So that's why it's called rectified linear unit. Basically, it's just only linear for the positive part. So ReLU, if we look at that, is a derivative function. We need to do backward propagation, right? So we always want some derivative function. This is a derivative function and allows for back propagation while simultaneously making it computationally efficient. ReLU is very efficient because it's linear. It's linear in positive x. So if we look at the linear part, actually the derivative is 1. It's unlike the sigmoid. If you want to get the derivative of sigmoid, actually you need some time. It costs time to compute it. But here, anyway, the gradient is 1. Very computationally efficient. And even if you do the forward propagation, it's still efficient because in the forward propagation, you just need to return this max between 0 and x. So the ReLU, we know activation function is used to activate neurons. If we use ReLU, then that means the neurons will only be activated if the output, deactivated if the output of the linear transformation is less than 0. So that means for each of the neuron, if the weighted sum, if the linear transformation is less than 0, then the ReLU outputs 0. So ReLU deactivates such neuron. Only if the weighted sum is larger than 0, ReLU will activate it. This is the mechanism of ReLU activating neurons. And it accelerates the convergence of gradient descent due to its linear property. If you use ReLU, it's very fast to train a neural network compared with other activation functions. But there must be some limitations, right? It cannot be perfect. It cannot be efficient while in the meantime, no limitation. There must be some limitations. And the limitations of ReLU is called the dying ReLU problem. Let's try to have a sketch what is a dying ReLU. This is the derivative of ReLU. The left side, if x is negative, then the derivative fx prime is 0, right? If x is positive, then this part has a derivative 1, fx prime is 1, because it's linear. The value is linear, then the derivative is just 1. So that means the negative side of the graph makes the gradient value 0. And then you can try to imagine during the backpropagation process, the weights and biases for some neurons are not updated. As long as the derivative is 0, then according to what we talk about gradient descent, the gradient descent depends on the derivative to do updating. That's the delta arrow function E, right? Delta E. If the gradient is 0, then actually the corresponding parameters, they won't get updated. Then it will cause some dead neurons. Dead neurons mean that, okay, in some forward propagation, the weighted sum is negative. Then in the backward propagation, these parameters won't get updated. Now since they are not updated, so it's very possible that later on in the future steps, they still get the negative weighted sum. And then ReLU won't activate them, and ReLU won't update parameters for these neurons. So it will as if the neurons are dead. So they are just some dead neurons which never get activated, because their weighted sum may just be 0, negative, and then the derivative 0, never activated, never updated. So all the negative input values become 0 immediately, which decreases the model's ability to fit or train from the data properly. So this is what we call the dying ReLU problem. And for this dying ReLU, it's actually it happens a lot, but still later on you will see that possibly next week you will see that even though the ReLU has the dying ReLU problem, but still ReLU is preferable, because ReLU can try to address some other problems of other activation functions. And again, actually we really like the property of ReLU that it's very efficient, it's very fast. So that's why in this neural network, we still use the ReLU as activation function in all of our hidden layers. All right, so any questions so far regarding the ReLU activation function? Great, if no question, I think the time is almost up, so let's just stop here. In next class, we will continue to introduce the softmax activation function and also how to build the model. And by the way, tomorrow is the deadline for PA1 submission. So please remember to submit your PA1 in time. And for the next week's lab, next Monday and next Tuesday, it will be midterm Q&A. We don't require your attendance. If you have any question, you can just feel free to go to the midterm Q&A to attend the labs. But if you don't have any question, you can just feel free to skip the lab. We won't take your attendance. Okay, and please have a good review for your midterm exams. Good luck to everyone, and see you in next class.